So this is an important question which gets asked to every power electronics engineer, designer, whether to use MOSFET or to use IGBTs for specific applications. So to understand this question a little better and then be able to answer it more completely, we would first quickly see the structure of MOSFET and that of IGBT and see what is the major differences between the two. So on the left side, I have already drawn the structure of a MOSFET, okay, which has a source terminal, which has a gate. Then yellow is the gate oxide. And then you have layers of NNP material and finally to the drain. On the right side, you see the symbol of the same N-channel MOSFET, which is drawn on the left side. And let's say that we have connected a positive source and a resistance between the drain to source terminal. And we have also supplied a positive voltage to the gate with respect to the source. So if gate has positive voltage, in that case, in this P layer, electrons come and settles very close to the gate. Now, if drain is at a positive potential with respect to the source, current will try to flow from drain to source. In other words, electrons will try to flow from source to drain. So if an electron from the source enter this N region, then this channel is also there formed of electrons. So this electron goes through here and then it through N minus and N region, N plus region, it finally comes out. So this is how the MOSFET conducts in the on state if you apply a positive gate voltage. However, if you do not apply a positive gate voltage, so now let's say the gate voltage is not applied. In that case, in this structure, from drain to source, current cannot flow. On the other hand, drain is still positive voltage and source is still negative voltage. Right? So this P and this N, this PN junction essentially blocks all the voltage between applied from drain to source, because this N and N minus region will not block. So the junction between P and N blocks. So in the blocking stage, or essentially when the device is in the off state, in other words, when the V gate to source is, let's say, equal to 0 volt, right, or anything less than the threshold volt. In that case, you have this depletion region which is formed between N minus NP region, right? So this is the depletion region which gets formed. The length of the depletion region depends on how much voltage you want this device to block. So if you are talking about a MOSFET which is rated for 100 volt versus another MOSFET which is rated for 200 volt, that means here you only need to block 100 volt. In the other case, you need to block 200 volt. So you need a larger value of depletion region in this case as compared to the first case. And therefore, as the voltage rating of the MOSFET increases, if you see 100 volt, 50 volt, 200 volt, 250 volt, 300 volt, as the voltage rating, blocking voltage capability of the MOSFET increases, the depletion region length L also increases, right? So and let us quickly have a look back into what is the impact of increasing L. The L is essentially comes into picture when you turn on the device, the same device when you turn it on by applying a positive gate voltage and it starts conducting. Then the electron has to travel longer distance in this N minus region. And the resistance, therefore the resistance of this N minus region increases. In other words, as the voltage rating increases, the L value increases. L is the depletion region length, and thereby increasing the resistance during the on state, right? Or the RDS, as we call it more popularly, RDS on. And therefore, it's very common that you would see a higher voltage device having a larger on state resistance. Now, the problem was that as we build 50 volt, 100 volt, 200 volt devices, it's okay, the resistance keeps on increasing, which is what we understand. But beyond a certain point, the resistance becomes significantly large, right? So imagine a MOSFET of 1200 volt. The resistance would be so big that it would incur significant amount of conduction losses. And that is the reason IGBTs are used. So let me show you the fine difference between IGBT and MOSFET and how that difference takes care of this particular problem. So still this is the structure of a MOSFET. Now I would make a minor change in this structure to make it that of an IGBT. I would replace this N in the bottom and instead of that put a P here, right? And of course, as I do that and I start calling it IGBT, which stand for insulated gate bipolar transistor, I change my terminology for drain as well as source also. Instead of calling it a drain, maybe now I will start calling it a collector, and instead of calling it a source, let me call it emitter. So what is the effect of changing this bottom N layer to a P layer, right? How does it help? How does it help in the context of reducing the on-state resistance? All right, let's see it. So let's first talk about the blocking stage. In the blocking stage, the same thing would happen. This PN junction would still block all the voltage that is applied. So it would still develop a depletion region around it, and the length of this depletion region determines how much voltage you can block. So the same process, higher the voltage you want to block, you need larger value of L. So far it's the same, right? Higher voltage blocking implies larger value of L. So if you want to block 200 volt using a MOSFET versus an IGBT, maybe you would have comparable values of L, and therefore during the on state, when the current is flowing, when the electrons are going from here to here, when the electrons are going from here to here, in that case you see the length of this N minus region is the same, so the resistance of this region may be more or less the same value. However, there are two differences that has happened. The first is, now in the on state there is a PN junction barrier, this barrier, the bottom one, which gets added. So instead of only a resistance, now you need to model the on state drop as a resistance and a voltage drop, let's say about 0.6 to 0.7 volt of a PN junction. That is one thing which is different going from MOSFET to IGBT. Now you would think that, anyways the problem was that resistance was large value, and that is the reason I was looking for alternate solution, but here you are in fact adding one more voltage drop of 0.6, 0.7, so it doesn't make sense. But then the other phenomena helps us reduce the value of R. The other phenomena is called as conductive modulation. And this is how it helps. So what conductive modulation does is, when this device is conducting, some of the holes from this P region enters the N minus region, and these holes also contribute to the conductivity, and these reduces the resistance of this channel. So effectively the resistance of this channel, which is R, reduces, as compared to the original resistance because of the presence of extra holes. Earlier you may remember that in the MOSFET you have N region. So this N region will not lead to injection of holes, but this P region now leads to injection of holes, right? And that is also the reason why IGBT is called as a minority carrier device. This is also the reason why IGBT is called as the minority carrier device. Right? Because in this N minus region, these holes are in minority and they are also carrying the current. So there are two phenomena that are happening as we are moving from MOSFET to IGBT. One, the channel length resistance is, the N minus region resistance is reducing, but then the PN junction potential barrier of 0.6, 0.7 volt is getting added. So how does it, I mean, both are contrary, both are opposing forces. So let's see how effect of one of them becomes dominating when we talk about a certain voltage and current rating, and how the effect of the other one starts dominating in the other case. So let's look at the case when we are talking about very hypothetically high voltage applications. Now if you're talking about very high voltage application, that means the L value of L is very large, right, to block that voltage. Therefore the value of R is very large. Now imagine that if something can reduce your R by 5% or 10%, and even there's a 0.6, 0.7 volt addition drop, maybe overall situation would be improving, right? And therefore in this case it makes perfectly fine if you have this kind of a structure during conduction, where the value of R can be reduced by conductive modulation, but then you get 0.6, 0.7, but which is fine. So usually for very high voltage and current applications, IGBT would give you smaller overall voltage drop and thus smaller conduction losses as compared to the MOSFET. On the other hand, if we talk about low voltage applications, in low voltage applications the value of L will anyways be small, the value of R will also be relatively small. Now if you add 0.6, 0.7 volt, that could contribute to a substantial increase in the voltage drop. And therefore generally for low voltage applications, a MOSFET offer less voltage drop or conduction loss, so to say, as compared to IGBTs, right? And that is the reason whenever we whenever we talk about, let's say this axis is current, this axis is voltage, right? When we talk about low voltage region, we usually prefer MOSFETs. And whenever we talk about higher voltage regions, we prefer IGBTs. Of course, there could be a small region of overlap as well. If you see practically, this region or the boundary is somewhere between 600 volt. So below 600 volt, you would see MOSFETs being popular. Above 600 volt, IGBTs being popular because in their respective regions they give smaller conduction losses. The other aspect of selecting between the IGBT and MOSFET is also the switching frequency, right? So first we studied is the conduction loss. What about the switching speed or the switching loss? So if we talk about switching speed or switching losses, in that case MOSFET of course does much better than IGBTs. And the reason is that in IGBTs, as we have seen, because of conductive modulation, there are some holes which are present in N- region. So when you turn this device off, these holes continues to conduct for some more time. and that leads to the flow of what we call it as a tailing current. So turning off a MOSFET could be very fast. Turning off an IGBT takes more time because of the presence of these minority carriers. So in terms of switching speed or switching loss, MOSFET does much better. And therefore, for low voltage applications where the conduction loss is also low in MOSFET, switching loss is also low, we prefer to use MOSFETs. Going at higher voltage, higher current regions, we would prefer to use MOSFET offering a higher switching frequency, but we don't use them because of the higher conduction losses. And therefore, we do a reasonably good compromise by using IGBTs, where we switch them relatively at lower speeds, but at the same time get low conduction losses as well. So that's the main difference between MOSFET and IGBT. That is the reason you would see popularly below 600 volt, lot of packages of MOSFETs available. Above 600 volt, lot of packages of IGBTs which are available.